Hey everyone, welcome back to your research buddy. And in this lecture, we will talk about formation of energy level in solids. Okay, how energy levels, how energy band is formed in solids. We will talk about in this lecture. So for that case, let us consider an isolated atom. And we know that in an isolated atom, electrons are tightly bound and have discrete energy level. This condition we know that. So let us consider an electron in this particular atom. This is the atom we are taking, and this is the nucleus, and we are considering the electron is revolving around this nucleus. So for this particular atom, the electron have energy level E1. Let's say this is energy level E1 for this particular atom. Now let us consider one more atom and also have same electron as we have in first case. So I am considering another atom here with nucleus and electron, and also in this case energy level is E1, right? So now if these electrons are or these atoms are far away from each other, then energy levels of electron in first atom will be same as the energy level of electron in second atom. Let's say this is my first atom and this is second atom, and if these two atoms are very far away from each other, then the energy level of first atom is equals to the energy level of electron having in second atom, right? So but when these atoms bring together, okay, so let's consider another state, the state 1. This is state 1 when two atoms are far away from each other, right? And in that case both atoms having energy level E1 and E1. Okay, now let's consider state 2. I'm going to take state 2 when in this state 2 we will bring together these two atoms, or these two electrons are now bring together, then what will be the resultant energy of that system? So when we bring these two atoms close to each other, they form an interacting system. Okay, so let's say this is my atom 1, and here we are having atom 2, nucleus, and there is let's say electron, and there is electron of second atom. When we bring these two atoms close to each other, they will form an interacting system. This is right now interacting system. Okay, this is our interacting system when we bring two atoms close to each other. So due to this interacting system, their wave function starts to overlap. Now we know that electron is revolving around the nucleus, so there must be wave function associated with this electron, and the wave function we are representing with psi, right? So this psi representing wave function, and when we bring two atoms close to each other, their wave function starts overlapping, and energy of these two electrons will no longer be same. As we have in state 1, the energy levels for atom 1 is E1, and also energy level for atom 2 is E1. They have same energy level, but when we put these two atoms in an interacting system, their energy level will no longer be same, and this is in the accordance with Pauli exclusion principle. Okay, so this is not our own statement. This statement is given by Pauli exclusion principle, and according to this principle, no two electron in an interacting system have same quantum states and hence same energy. It means energy of electron 1 and electron 2 is different. So this result in splitting of energy levels. So that's why from this E1 state from this E1 energy level of atoms, due to their interaction, the splitting of energy level will be there, and this splitting of energy level will be very close to each other. Okay, so there is a formation of energy level E1, and very close to this one there is formation of energy level 2. There might be some difference between these two states, but they cannot be equal when we put atoms in an interacting system, right? Similarly, if we bring three atoms close to each other, second atom and third atom, their nucleus, electrons revolving around these, so there is the formation of possible three energy states: E1, E1, E2 and E3, right? So this is just an example of 1 2 3 atoms, but in a solid we have n number of atoms. So what if we bring n number of atom close to each other, then there is a formation of n energy levels, right? So this splitting of single energy level into n number of energy level lies very close to each other, result in the formation of energy band. So there is if and the splitting of single energy level by putting all the atoms in an interacting system. Like I'm taking example of a solid material. So in a solid material, in a crystalline material, there is n number of atoms. So if we put all these atoms close to each other in an interacting system, they will split into n number of energy levels, and these energy levels lies very close to each other, and this will result in the formation of energy level. So this is how energy level is formed. Okay, so again, how energy bands are formed. So we can simply written it as energy bands are formed due to splitting of single energy level into n number of energy levels, because n number of atoms form an interacting system when they come close together to form a solid, right? And also we can represent this by using a diagram between energy and, so let's say we are taking this side energy along y-axis, along x-axis what we are taking, inter-atomic distance. Okay, because what we are talking about, if we put any two system close to each other, what we are changing, so the distance between these two atoms is represented by inter-atomic distance. Okay, so if we change the interatomic distance, automatically that system will be in an interacting interacting state, right? So we are plotting a graph between interatomic distance and energy, and if the interatomic distance is very large, interatomic distance is very large, then there is only single energy level as shown here, right? But further reduction in interatomic distance, atoms will start interacting with each other and their wave function starts overlapping, and due to this overlapped wave function, there is a formation of n number of energy levels, right? So there is a formation of this single state will split into n number of energy levels, and at what point we can change or reduce this interatomic distance, at what level we can reduce. So there must be a point that is called equilibrium interatomic distance. Till this point we can reduce the interatomic distance, and there is a formation of n number of energy level. So to form a solid, large number of atom brought together, and as we bring atom close to each other and close to their initial quantization energy level, these energy level will split into a band of discrete energy levels, right? And the energy level can brought closer till the equilibrium interatomic distance. So let's try to understand the formation of bands by using an example, and we are taking example of carbon, right? And we know that carbon having electronic configuration is 1s2, 2s2, 2p2, right? Now here 1s and 2s levels are completely filled, and 2p level is partially filled, right? So now if we bring if we bring all these states closer to each other, there will be formation of n number of states. And now let's consider what we are taking. This side we are taking inter atomic distance, and towards that side what we have energy, right? And when the distance is very large, there is 1s state. After that we are getting 2s state, and then there is 2p state, right? And here when we reduce the interatomic distance, there is splitting of this s state, and this s state can split into 2n states. Okay, so there is a splitting of 2n state of this s state, 2n states. So this s state can split into 2n states. And how many electrons are there right now? If we are taking example of carbon, there are 2 electrons, right? We have again 2s state, so this 2s state can again split into how many? 2n states, and this is also filled, so we have 2 electrons here. Now p state can split into, as we know that in p subshell how many electrons are there? 6. So this state can split into 6 subshells. Okay, so there is 6n states in this case, but right now how many states are filled for this case? 2n states are 2 electrons are filled in this case, right? 2 electrons are there. Okay, right? Now further reduction in interatomic distance. Okay, so further reduction in interatomic distance, the splitting of these states happen, and 2s and 2p states are very close to each other, so they will start merging with each other. So further reduction in interatomic distance, the states of this 2s and 2p, as this principal quantum number is 2, so these states are very close to each other, so their wave function will starts overlapping with each other, right? Okay, so these states starts merging with each other. Okay, and due to their merging of these two bands, we will get single band. And now the band is having how many states? So this particular region, there is a region of single band, right? Further reduction in interatomic distance. Initially we have this state and this state, that is 2n state for 2s and 6n state for 2p. But as we reduce the interatomic distance beyond a point, these two states will merge with each other, and there is a formation of how many states? 8n state. At this region, how many electrons right now? We have 4 electrons are there. It means 4n states and 4 electron at this particular point. And further reduction in interatomic distance, the field energy level will be separated from the empty energy levels. This is very important point. Further reduction in interatomic distance, here again I am representing this again and again with this arrow, that interatomic distance is reduced toward this side. Okay, at this particular point, we have 8n states and 4 electrons according to carbon configuration. But further reduction, as we moving interatomic distance from this point towards the lower interatomic distance, the field energy level is getting separated from empty energy level. Okay, right now the equilibrium interatomic distance is this one. This point will become equilibrium interatomic distance, right? And there is a splitting into 4n state and 4n electrons. So as we have discussed, field energy level is getting separated from empty energy level. We have total state n state, 8n state. Okay, so out of these 4n state are filled, so it means this part is getting separated. This is field energy level, and this is empty energy level. In that case we have 0 electron, and here we have 4 electrons. So this gap between these two states, the state between these two states is called forbidden gap, forbidden energy gap or forbidden energy state, right? Okay, so in first state all the energy levels are completely filled, and thus then there is no separation between state. Why this 1s state is not getting separated into a different energy level? The reason is that in that case all the electrons are fully filled. Okay, so there is only one energy band, that is fully filled energy band. The separation only happen when we have fully filled as well as partially filled energy level in a single quantum number. Like we have single quantum number 2s 2p. 2s is fully filled but 2p is not fully filled. So in that case, further reduction, further interaction, the splitting is going to be happen between fully filled energy level and partially filled energy level, and due to that they will get separated and there is a formation of energy gap between these two. So this is how energy level is formed, and we can call uppermost level. This level is now named as, that is in that case we have no electrons. This is called conduction band, conduction band. And the state when all the states are fully filled, this is called valence band, valence band and conduction band, right? So the uppermost band is named as conduction band and lowermost band is named as valence band, and the distance between valence band and conduction band is known as forbidden gap, or band gap or energy gap, band gap, right? So this is how energy levels are formed. I hope you are able to get it. If you have any question, you can comment below. Thanks for watching this video. I'll see you in the next one. Thank you.